Okay, welcome to part 2. So now we're going to look at the other part of the electromagnetic force. Remember, electromagnetism is a force associated with charged particles. So in electricity, those charged particles can either be separated from each other, forming static electricity, or they can be running through something and forming a current of electricity. And mostly, when we talk about charged particles, it's really the electrons that we're concerned with. Electrons have this freedom to move because of where they are in the atom and the fact that they're really small. And so we can move electrons around and do special things with them. Magnetism is not seen as often as electricity by most people, and that's because there are very few substances that are actually magnetic. What makes something magnetic? Magnetism, it turns out, is caused by something called spin. Electrons are particles, and those particles actually rotate. They spin on their axis, the way the Earth does, causing day and night. This spinning is what creates magnetism, because some electrons spin with their south pole up, and some spin with their north pole up. In most substances, this is a completely random arrangement, so that in any given atom, the electrons in it, some of them are pointing up, some of them are pointing down. And it tends to balance out perfectly because of something called paired electrons. Here's an iron atom. The electrons are shown in all these different levels around the nucleus, which is shown in green. And I have 3 or 4, actually, red electrons. See if you can find them, right? There's a red electron over here. There's one over here. There's one here. And there's one here. And what's different about those electrons in the iron atom? Well, you might notice they don't have partners. They're not paired up. All the other electrons are paired up with each other. When electrons fill into an atom, when they get attracted to an atom, and they're attracted to the positively charged nucleus, when this happens, they come in a particular order. They always come with one electron pointing or spinning with its north pole up, and one electron spinning with its south pole up. So they're said to have opposite spins. Now, it doesn't really matter what any of that means. What matters is, most of the time, in any given atom, most of the electrons are partnered up. They're paired. And when they're paired up, they're with their opposite. And so, they cancel each other out. Electrons are baby magnets. They're itty-bitty magnets. But their magnetic effect is totally canceled out by the fact that they're always hanging around with their opposite partner. Except for in a few rare substances, like, for example, iron. This is an iron atom. And it just so works out that in iron, there are these 4 unpaired electrons. And unpaired electrons are free to be magnetic. Pardon the bell ringing, scared me a little bit. So these free electrons are able to spin all in the same direction. Maybe they're all spinning north, maybe they're all spinning south, it doesn't matter. The point is, they have a cumulative effect. If I get enough iron atoms together in one place, I can feel the magnetic force of iron. There's only 2 other substances on the periodic table of elements that are magnetic. Cobalt and nickel are the other 2. This is just because they have a very strange, all 3 of those atoms have a very strange tendency to have these unpaired electrons. And unpaired electrons are magnets. So this is why most of the material in the world doesn't show any sign of being magnetic. It's because all of the magnetic charges in them caused by electrons, or all the magneticness, is balanced out perfectly evenly. Here's what it looks like in another picture. You might have noticed that iron is only magnetic if it's been magnetized. Just a regular piece of iron, like a nail or a paperclip or something like that, is not magnetic. And that's because just because a single atom of iron has some leftover magnetic force doesn't mean that all of the atoms are going to have that magnetic force all pointing in the same direction. What we have to do is we have to force every piece of every single atom in that material to spin the same way. To do that, we need an external magnetic force. Over here on the left, what I'm showing is what a chunk of iron metal pulled out of the ground normally looks like. It's got what are called domains, which are just ranges, little places where there's a clump of atoms that are influencing each other, and all of them in that section might be pointing the same way. And so they're like their own little magnetic area, but they're all pointing in different directions. All of the spins that those electrons have are going the same way, and that's whatever direction the arrow happens to be in. If we want those domains to all point in the same direction, we've got to expose the iron to something that makes that happen. And usually, ironically, that something is usually electricity. And this is how we finally figured out that electricity and magnetism are linked to each other. It turns out if you bring an electric field near something that can be magnetized, it will force all the electrons to spin the same way, like they are here. So you can make iron into a magnet, but it doesn't necessarily seem that way when you first pick it up. And you're going to see this as we do several labs. You'll see how you turn ordinary iron into an actual magnet. And what we'll do is we'll make it an electromagnet. And the way that we'll make that iron, all the domains line up, is by running an electric current around it. And that'll force all of the electrons that are free, that are unpaired, to spin the same way. So you might be wondering at this point, what's the takeaway here, Mrs. Stracuzzi? What is it that I should really know as an 8th grade student? Because a lot of this stuff is very higher level, right? Here's the basic thing. The basic thing is that magnetism is caused by electrons. Specifically, magnetism is caused by electrons that are spinning. And the spinning is shown in this picture of an electron right here with an arrow that's in black. See that black arrow there? That black arrow is showing you that this electron is spinning sort of to the right, or what we might think of as towards the east, the same way the Earth spins on an axis. The axis is the south and north poles. In this particular electron, the axis is straight up and down with the south pole pointing up. But any given electron can be pointing in any direction. It can be pointing to the left, it could be pointing to the right, it could be totally upside down, any which way. However, in most atoms, electrons pair up with each other. And the minute you have one electron facing this way, the electron that pairs up with it has to be the opposite way. This is the only way they get to pair up. And so you can see that the electron on one side over here is pointing with the south up. This electron is pointing with the north up. And notice that they're spinning in opposite directions. So this means that their magnetic force is canceled out because the direction you're spinning in is the direction of the magnetic force that you have. So these two electrons cancel out each other's magnetic force. But there are some rare elements, iron, cobalt, and nickel, that don't have all of their electrons paired up. They have a few unpaired electrons, and those unpaired electrons get to pick whether they're up or down, left or right, and how they're spinning. And as a result, those unpaired electrons are free to be magnetized and turned into a magnet, which usually happens using electricity. So the next thing we'll learn about is how electricity and magnetism cause each other or create each other and how they work together. See you in the next tutorial.